Okay, so this is video 3, lecture 3, and we just finished talking about making inferences from inside the data to outside the data using a bin model. Now in this video, we are discussing how does the bin model relate to my learning problem. If you remember, in our bin model, the unknown was my mu, right? And this is what I was like trying to determine. But in my learning problem, my unknown is this entire function f, the target function, that maps my input x to my output y. Right? So how are these two situations related? Because obviously I did all that I did in my previous lectures was to eventually do something for this, right? The two situations can be connected, and we are going to see how these two situations can be connected. Let us try to visualize that. So let us assume I have like the two-dimensional data for the credit card problem, if you remember from one of the previous lectures, right? So this is income and this is age, right? And let us assume that this is my target function f, right? So this is my target function f. Anything below this is a -1 and anything above it is a +1. Right? This is somewhat a pictorial representation of a target function. Let's say I have like multiple hypotheses. I have a hypothesis set, and one of the hypotheses looks something like this. Again, the same graph, the same variables, income and age, but my hypothesis H looks something like this, right? So this is one H belongs to that hypothesis set H, right? And again, this is +1 and this is -1. Okay, so if we take both this and we somehow try to come up with a hypothetical picture, obviously this picture wouldn't exist in real world because f is unknown, if you remember. But let's say I have this hypothetical picture where I superimpose, I take this and this, both of them, and put one over another, right? So income and age, and let's say this looks something like this. And then this guy, I think, is coming like this, right? And goes here. Okay, so the portions which are shaded, I'm just going to shade them like these ones after superimposing, are the ones where my H and F are not in agreement with one another, right? Because notice, this is like the +1 area here, but here it is in the -1. Similarly here, this is the -1 for this one, but actually that region is +1 for my H, right? So these are the shaded area is the one where H and F do not agree, right? Basically, I can put that in writing. I can say that this is the blank area is where my H of x is equal to f of x. That means they agree. And this is like I'm looking at a binary problem where plus and -1 are the only outcomes, right? So these are the regions where this is true, right? The blank regions. But the shaded ones are the ones where h of x is not equal to f of x, right? Okay. How about we think of all the training examples? So this is my bin, this is my larger data set D. How about we consider each training problems? These are like, there will be some points here, essentially, right? So I can consider this entire data set to be my bin such that the points that lie in the shaded region, right? So the points, let me write down, in the shaded region are the red marbles, right? And the ones that lie in the unshaded region are my green marbles, right? How about I just like try to represent that by red and green marbles so that I can draw an equivalence between the bin model and this learning problem model, right? So this, if this is red and this is green, what I'm really interested right now is that if I pick a random point, I'm really interested in the probability here of like finding the red, right? The probability of finding how many red marbles are there, or the probability of the probability of the fraction of red marbles, remember from the bin model, is essentially equivalent to saying that the probability when h of x is not in agreement with my f of x, right? This is what I'm interested in some sense, right? And this quantifies my error. This is analogous to my mu, right? So let me write it down. This is analogous to my mu, right? So now The training examples here will play the role of a sample from the bin. If the inputs like x1, x2, xn, and so on in D are picked independently according to P, we can get a random sample from this, right? We can get a random sample of reds and greens, right? Because what is going to be my reds and greens? My red is going to be, as I said, when h of x is not equal to f of x, and my greens are going to be when h of x is equal to f of x, right? The only thing is that when we are drawing a sample, all we have to be like really clear about is that they are picked randomly according to some probability p, right? But here, and another thing that we need to know is that this target function is unknown, right? So when we are picking points, when we are trying to get the sample, because remember in the bin model, we have the bin and then the sample. So again, we are trying to do the same here, right? We are picking independently some random points, but we don't know the real red and green, right? But what we know here is that because our h is our hypothesis, so we can evaluate any point, and my f x of n is y of n. Let me write it down so that it doesn't really messes with what we have built until now, right? So what we are trying to do is we will pick some random points to get some sample out from my data, right? And then the way I'm going to pick them up is it should be picked independently and randomly according to some distribution on X, right? That is let's say with some probability P. And the important point here is that we know we are like unaware of what my f of x is. However, from my data, I know that my f of x is some y, right? So this is known, right? So this is known, correct? And so this is how, like, this is given to us in the data set itself, right? So once we have all these, like, so to say, requirements, right, then my bin problem has been reduced to my learning problem. But it has not yet ended because we have to quantify a couple of things. For example, what is the true fraction of red in the bin? We have to still, like, that question is open and we have to find out. And here now I'm going to define some notation, and this notation is going to hold going forward. So now I know that the probability of when h of x is not in agreement with f of x that we saw here, right, was somehow representing my mu in the bin. But what happens in my sample? Now I've picked a sample, right? I've picked a sample. And so my disagreement, so to say, between h of x and f of x is essentially going to represent something that's analogous to my nu, right? So how do we kind of write that first of all? So from now on, what I'm going to do is, like, if we have picked a sample and we are trying to determine the disagreement between my hypotheses and my target function is known as the in sample error, and it is denoted by E of n, which is defined over a certain hypothesis h, right? Because this is the function using which I'm trying to determine whether my h of x is in agreement with f of x or not, right? And the way this is calculated is that first of all, I'm going to get an indicator function which is written like this. So this is essentially the outcome of this is a boolean, a yes or a no, or true or a false. When, like, count all those outcomes, right? This is what it means when h of x is not equal to y of n. So I just have translated xn, let's say I have n data points, and yn, right? So all those points where h of x, where my target, where my hypothesis is not in agreement with my y of n, count those. This is the indicator function, right? And once I'm done with that, it obviously will have sum over all the data points that I have and find the average of that, right? So this is how we define the in sample error, which is analogous to my mu in my bin model, right? And now the only thing that's left from the bin model is my the out of sample error, or my mu, because that was also important, and that is something that we are trying to get at, right? We are really trying to find the dependency of E in, right, this thing, to something that's outside of the data set but in the bin, right? And that is something that we define as E out. So the error outside my sample, the sample that I've picked to calculate E of n, right? We're trying to find the relationship between E in and in, which we'll talk about a lot going forward. But right now I'm just like trying to define that, which is nothing but the probability, right? It is like this is the probability in the bin, so which is the larger population, when h of x is not equal to f of x, right? So if we think about the bin model, it is those places when this shaded part, when they were not agreeing with one another in the bin. But now in the sample, obviously we would have picked a smaller subset, right, from the bin, and then compute the probability of h of x not equal to f of x. Okay, so having said that, and then let me write it down, this is analogous to mu, right? So having said that, how does like Hoeffding inequality plays in terms of these error terms? Because earlier we had like everything in terms of nu and mu, but now everything is different when we redefined or translated the bin model to my learning problem. Let's look at that. It's pretty intuitive, and this is how this comes into picture. So Hoeffding's in terms of error values, right? First of all, it is possible. What we are still establishing here, and we are continuing to believe that it is still possible to go from inside to outside with high probability for a learning problem as well, right? So for learning as well, that's why the Hoeffding bound stays with us, right? Uh, the other, like, so instead of, like, as I said here, this is analogous to nu and this is analogous to mu. So that's how the Hoeffding bound changes for my, like, for both the cases that we had earlier, right? So for the good and the bad, if you remember. So for the bad, instead of nu and mu, I have like E in calculated over some hypotheses h minus E out, right? Which has to be greater than my tolerance, which is epsilon, right? And I decide that should be less than this value, which is something that we already know for any epsilon greater than 0. So some finite error tolerance. Similarly, the probability of bad, again, nu and mu is replaced by E of in, error of the in sample error, and the out of sample error should be less than some epsilon, and this has to be greater than 1 minus, right? So this is just like the complement of this. So that's pretty intuitive. The only thing that, like, a few assumptions that we need to remember is that this E of in, which is like the in sample error, is random but known. E out is fixed, just like mu, it's fixed but unknown. This is something really important that's going to go on, and we're going to talk a lot about that going further in the course. But this is something that's known to us, right? We can definitely calculate that. We know that because this is analogous to nu, and nu depends on the sample. So similar to that, it depends on the data that we have, right? E of in or in sample error. Now, think about it. If E in, which is like the in sample error, is 0, right? And because this Hoeffding bound holds, right? So if my E in of h is almost equal to 0, because this is the good thing, this is what we want to happen, that my error should be as low as possible. This disagreement between h of x and y of n should be as low as possible, right? So that's a good thing. That is going to be a good model, and what kind of um, implies that this is a good model, right? If E of n is E in, which is like the in sample error, is like really, really small, this is going to imply, as a result of the Hoeffding's bound, that my E out of h will also be 0 with very high probability, right? So this is what it means, because now we have translated the bin model to my learning problem. And so I can say that if E of in, which is like the in sample error, is really small, then E of out, which is the out of sample error, can be like really, really small with very high probability, right? So we have this kind of tells us that we have learned something outside my data, the D that I have, and that outside is my target function, right? F. Also, like, just to add to what we have here, let's say if I get an E in, which is again in sample error, to be really, really big, if I have the in sample error really big, then I know that this is a bad result, right? And we can say that my target function does not quite agree for whatever like hypotheses I've chosen. and it's like not at all even close to H, right? This is not like, if you think about this as a result, this is not really useful, except that it's telling us that F is obviously not close to H, but then there are like so many H that we could have come up with, right? So the unknown is huge in this case. And so this is not really something useful, but this is what it tells us if my error or my in-sample error is huge. Okay, so now we've established a relationship between the bin model and the learning problem. And now instead of nu and mu, I have the in-sample error and the out-of-sample error. And let's kind of try to summarize both of them, right? Function versus bin. So this is like the learning problem, and then this is the bin model, right? This was the picture that I was trying to basically draw. So if this was my target function and this was my hypothesis, this is what this is where like they agreed, and in the red region, both the functions did not agree. And this was my sample. And as you can see, if I picked these points and trying to calculate the error term, this is how I'm going to calculate. And this actually translates, if these red points were picked from the area that did not kind of agree to one another, then basically what I was calculating was these number of points where there was this disagreement, as you can see here, and then just like counting them and dividing them by the total. And this was exactly the same thing as I did here. If this was the sample that I picked up from my bin, right? So this is my bin here, right? The superimposition of my target function, which is obviously unknown, and my hypotheses, right? But in the sample, I know that because I have the y's. So just like a reminder, in my bin model, all I was doing was randomly drawing that sample and calculating my nu. Here I'm counting the number of disagreements, and that's how I'm getting an E of in, which is nothing but the in-sample error. And this is the analogy that I can draw from mu, which was the fraction of red marbles in the sample. Similar to that, I have something known as out of sample error, or E sub out, which has like analogy similar to my mu, so that my mu was something that determined the probability of picking a red marble in the bin. It was fixed, but I did not know it. Similar to that, this out of sample error is something that is determining the probability of getting this disagreement here, right, in my original bin, in my actual thing, right? But the issue here again is that it is fixed, but it is unknown, right? So this is how we can relate the bin model, or rather translate the bin model to the learning problem. A lot of things stay the same. A lot of things simply translate to a point to a function and so on. But this really helped us understand this translation from a bin to like creating this learning problem, and also coming up with terms like the in-sample error and the out-of-sample error. Okay, so in the next video, I'm going to talk about something that's known as verification and how is it different from the learning problem and how we're going to build on that. Thank you.